Have you ever stopped to think about how we actually write numbers? We use 10 digits, 0 through 9. But the computer you're watching this on, it only uses 2. So how in the world do these completely different numerical languages work, and how do they even talk to each other? Well, let's dive in and figure it out.
And this is really the big question, isn't it? I mean, it seems kind of impossible. How can a system that only has 2 symbols, a 0 and a 1, create, well, everything? The entire digital world? That's exactly what we're going to break down.
So, to really get a grip on the computer's world, we've got to start with our own. And the number system we use every single day, probably without even thinking about it, is called the decimal system.
Our system is called base 10, for a pretty simple reason. It uses 10 unique symbols. But the real secret sauce, the magic, is this idea of positional value. The 9 in the number 900 is worth a whole lot more than the 9 in the number 9, right? And that's all because of where it's sitting. Okay, let's take the number 294. We just automatically know it's 294. That's because we get that the 4 is in the ones place, the 9 is in the tens place, and the 2 is in the hundreds place. Each spot is worth 10 times more than the one to its right. It's totally intuitive to us. We don't even have to think about it. All right, now let's switch gears. We're going to step out of our world and into the computers. If we live and breathe in base 10, well, computers live and breathe in a system called binary.
And I mean, just look at the difference here. Our world has 10 different digits to play with. The computer's world is just brutally simple. 0 and 1. That's it. Everything a computer does, from showing you this image to playing your favorite song, has to be built using just those 2 symbols.
So why is that? Well, at its most basic physical level, a computer is just a massive collection of billions of tiny electronic switches. A switch can either be off, which we call a 0, or it can be on, which we call a 1. There is no in-between. So you see, binary isn't just some random choice. It's a direct reflection of how these machines are actually built.
And every single one of those zeros or ones gets a name, a bit. It's just short for binary digit. And it's the absolute smallest, most fundamental piece of data in all of computing. Every photo, every document, every single letter on this screen, when you get right down to it, is just a giant, long sequence of bits.
So how on earth do we read this stuff? Converting from binary to our system seems super intimidating, but there's actually a pretty simple trick. Let's take the binary number 1101. Just write the numbers 1, 2, 4, and 8 above the digits going from right to left. Now, all you do is add up the numbers that have a 1 under them. So that's 8 plus 4 plus 1, which gets you 13. See? Not so scary after all.
Okay, so binary is perfect for computers. It's simple, it's direct, it matches their hardware, but for us humans, oh man, it creates a huge problem.
Just look at that. That is a single number. Can you tell what it is just by looking at it? Could you type that whole thing without messing up? Probably not. It's just a wall of ones and zeros.
And as this source points out, it's not just you. Binary numbers are incredibly long, they're awkward to work with, and they are super easy for us humans to mess up. Can you imagine trying to find one tiny mistake in thousands of lines of that? It would be an absolute nightmare.
Yeah, it looks complicated because for our brains, it is complicated. And this was the exact challenge that early programmers were up against. They desperately needed a better way to work with the computer's native language without going completely nuts.
And that brings us to the really elegant solution. Instead of trying to reinvent the wheel, they came up with a clever shorthand to make binary readable for humans. So say hello to octal and hexadecimal.
So here's the game-changing idea. Instead of trying to read that long, scary string of ones and zeros as one giant number, what if you just broke it up into small, bite-sized chunks? That one simple insight changes everything.
And this is exactly where our 2 new systems come in. The octal system groups those binary digits into chunks of 3, and the hexadecimal system, which is way more common today, groups them into chunks of 4. Now, what's really important to get here is that they're not replacements for binary, they're just a human-friendly way to read it.
Think of this thing as a secret decoder ring. Since hexadecimal groups bits into 4s, we actually need more than our usual 10 digits to represent every possible combination. So, what do? Simple. After 9, we just use the letters A through F. Each letter is just a nickname for a specific 4-bit pattern. A is always 1010, F is always 1111, and so on. It's just a lookup table.
So let's go back to that terrifying wall of numbers from before.
If we break it into groups of 4, 1101, 1010, 1111, and 1110, and then use our new decoder key, that long, ugly string becomes the simple, clean, and totally readable hexadecimal number, DAF. I mean, come on, that's so much easier to write down and remember.
So, we've looked at a few different ways of writing numbers, and each one plays a really specific role in how we humans talk to computers. Let's do a quick recap just to put it all together.
Here it is, all in one place. You've got decimal, which is base 10, that's our everyday system. Then there's binary, base 2, the computer's true native language. And finally, octal and hexadecimal, base 8 and base 16, which are really just the convenient shorthands, the translation guides we use to make binary easier for us to understand.
And this really gets to the single most important takeaway here. The computer has no idea what hexadecimal is. It doesn't care. It only knows on and off, 0 and 1. Hexadecimal and octal are tools built entirely for us. They're a translation layer, a human-friendly interface to make the computer's world a whole lot less intimidating.
Which leaves us with a pretty interesting final thought to chew on. We created these systems to make sense of the machine, but in the process, we've had to learn to think in a much more structured, logical way, a lot like a computer does. So the question is, are we teaching the machine